Okay, let's start. Okay, so we were discussing about the current mirrors. So basically, the very intention of current mirror is to ensure to replicate the amount of current that is being given here as a reference into this particular wing. So that was basically our intent, and this is what we started off with, the basic current mirror, where we first figured out the output resistance. And because it is going to act as a constant current source, that means it should have its the output resistance to be high. And we figure out what is the output resistance over here using by applying the AC supply over here. We did the AC analysis and we figured out the AC resistance. Then we figured out for a particular value of W and L, I'll get some value of resistance, which obviously should be large. And for that value of resistance and for the fixed value of W and L, I'll be ensuring that the same amount of current which I'm giving here as a reference would be flowing over here. Now, what I did after this, we moved into the next level of current mirror, which is cascode current mirror, wherein we stacked the transistors one above the other, something like this. Now, this had an extra advantage where we were able to see effectively more output resistance with the same set of topology by just adding additional MOSFETs. Obviously, by adding additional MOSFETs, we are going to increase the area of the entire circuit by small amount, but the level of output resistance it is going to give is tremendously large, and that is beneficial for my current mirror. Now, the reason for getting into the stacked concept than the current mirror is obviously we cannot keep on increasing the size of a single MOSFET to a larger extent. Like basically, I cannot keep on changing W and L to a greater value to see a larger resistance value over here. So there is always a limitation. So what I did value of W by L. See, if you see W and L are having a value of 10, that is the ratio is W by L is 1. So here also I kept the same ratio, but on top of that I added one more stacked MOSFET. I stacked one MOSFET. So this obviously increased an area to a small extent, but this had an advantage of getting in added output resistance over here. So now in this session, we will get into the concept of what is known as low voltage cascode current mirror. Now, what exactly we mean by low voltage cascode current mirror? So basically, the current mirror things will actually work as a current mirror basically when the main MOSFETs which are over here, like, or basically if I go into this current mirror, simple current mirror, this MOSFET has to be pushed in the saturation region. When this MOSFET is pushed into saturation region, then a constant current starts to flow. Now, at what voltage this MOSFET would be pushed into saturation region would define the the time, or would define the value of voltage at which this particular entire current mirror is going to behave as a constant current source. So basically, let's say if this MOSFET is getting pushed into saturation region, let's say at 800 millivolts, that means up to 800 millivolts, I'm not able to see a constant current in this peak. That means my this particular circuit would behave as a constant current source, or current mirroring action would be performed only at a saturation voltage of 800 millivolts, which is going to push this MOSFET into saturation region. So that is basically when I mean pushing this MOSFET into saturation region. Similarly, for a cascode current mirror, I will be ensuring when does this MOSFET would be pushed into saturation region. That is going to define the voltage at which this particular circuit is going to behave as a constant current source or current mirror circuit. Similarly, when I talk about low voltage cascode current mirror, we need to understand why it is called as low voltage, and also we need to see at what voltage this particular MOSFET would be pushed into saturation region, so that I'll be able to see a constant current, which is a replica of this current in this particular wing. So let's try to do those entire exercise. So before that, let us now try to run this cascode current mirror once. So anyhow, I have the schematic with me. So let's try to run this cascode current mirror, and let's see at what voltage this is going to be entering into saturation region. So the schematic is already ready. So I'll just go straight forward with the execution. We'll go into the launch ADL. Now here, before that, if you see, these are the AC supply. This is a sinusoidal signal which I have taken with a DC voltage of VDS, which I'm going to mention over there in the ADL window. And AC magnitude is 1. This will help me to calculate the resistance. So that is the value that I have taken. Other than that, I have, let's make it as VDD as 1.8. Yeah, and here I have taken a current source, a reference current source of 10 microampere, and everywhere I have kept the values of W and L as 10 micrometer. And why I have taken this 10 micrometer, we have already seen for a particular value of W equal to 10 micrometer and L equal to 10 micrometer, I'm going to get a larger output resistance, and that's why we have fixed up these values of W and L. Okay, let us try to. So let's push in the value of BDS to 900 milli, and then let's first try to do the AC analysis. Run it for from frequency of 1 to 1 gigahertz, and then outputs to be plotted. So this is my output current which I need to figure out. See what I'm going to do it over here with an AC analysis. There's an output current, there's a voltage being applied over here. This voltage divided by current would obviously give me the resistance in this particular wing, which is my output resistance that I'm going to figure out. So let's run it. Yeah, so this is basically your current in terms of frequency, but I want the 1 by x. So basically this, what is the value of this? Basically, you see, this is I versus frequency. This is basically the current. So the if I take, I'll just do this. I'll just send it to the calculator. So if I do the inverse operation of this particular function, 1 by x, and plot it. So if you see, this will be my output resistance. So maybe we can note it somewhere. So it is 347, almost 347 mega ohm. 1 by A means 1 stands for that the magnitude of the voltage. A is your unit of the current. V by A, that is volt by current, which is nothing but by R. So that's my mega ohm. So 347 mega ohm. Let us try to minimize this. And also, this is one thing. Let's try to even get into the figure out what is the region of operation. So basically, at what particular voltage this cascode current mirror is going to enter into saturation region. Let's try to do that also. I'll change this plotting mode to new window. Go to the output setup. So I need to find out region of operation for upper transistor. Just I name the expression and I'll click on the expression. I'll open the calculator once again. I'll clear the calculator. And this is an OPT option here. I'll click on this. The moment you click on this, it will redirect you to the same schematic window. And you need to select this particular MOSFET for which we are going to find the operating region of operation. Once I click this, come down over here and search for region. Region is here. Yeah, and then go to this setting what we have done, and they say get expression. So this is the expression we got, and they say add, it will be added over here, and I say okay. When I do this, I'll just close these things. When I do this, if you see here, ROP is being added, and this we have done in the current mirror concept as well. Let us try to do the same thing for ROPN. I'll open the calculator once again. So anyhow, I have the expression over here. Let us try to see what MOSFET we want to have. So I have the region of operation for my upper MOSFET as NM3. For my lower MOSFET, it is NM1. So I can easily just change here to NM1, or even I can just say, I'll go into the setting and I'll say get expression NM1 because I changed over here. So that came over here, and I say add, I say okay, and say close. So now I don't need, now I need parametric analysis. I need to be doing that one. But before that, so I have pushed in the ROP and RON. Before that, let's try to do the DC analysis once to figure out whether 10 microampere is getting populated here or not. Go to the DC analysis. Select component vary parameter, component parameter, and select this voltage, EDC. 0 to 1.8. So for time being, I'll disable the DC analysis, and I'll even disable these things, ROP and ROPN. I'll just try to do the DC analysis, which is going to get me the current. Hopefully, it should give me the current, constant current. You see, a constant current of almost 9.9, which is 9.8 microampere, which is close to 10 microampere. So basically, it is going to behave as a constant current source. That is fair enough. That is done. So now I'll enable these things ROP and RON, and what I'll do, I'll get into the parametric analysis. So go to tools, parametric analysis, and I need to sweep the variable for bring this parametric sweep, this BDS, from 0 to maximum mole value of 1.8, and the steps would be linear steps, and I'm going to do this sweeping from 0 to 1.8 in a step of 0.1. Let's run this. So once I run this, I'll be obviously able to see two small curve, which is going to tell me the region of operation for both the, yeah, you see. So this indicates the 400 millivolts is the voltage at which ROP, it should have been D down. So that is basically the down transistor. And if you see here, almost equal to close to 700 millivolts. So that means when 700 millivolts comes, my upper transistor will be entering into saturation region. And when 400 millivolts come, my below transistor will be entering into saturation region. But when do I say that? When both the transistors will be entering into saturation region? See, at this particular point, my red transistor, which is my upper transistor, would have not entered into saturation region. So basically, up till this particular value, the upper transistor will never enter into saturation region. So basically, at this particular voltage, if I just want to mark it over here, so at this particular value, close to 700. So at this exact value, both my MOSFETs would be entering into saturation region. So that means both my upper and below transistor would be entering into saturation region, and then only I'll be able to see a constant current over here. So that means the minimum voltage at which this particular cascode current mirror is going to behave as a constant current source or current mirroring action would be performed, that would be at a value of 700 millivolts. So that is basically the thing. So this is basically we figured out from the cascode current mirror. On the same lines, Let's close these things. On the same lines, let us now try to figure out and understand how does the low voltage cascode current mirror would work. So before that, let me close this ADL window. I'll keep the graph as it is. Let's try to understand this schematic. I have two transistors in the same way as that of your cascode current mirror. If you see over here in the same manner. And then I have an additional MOSFET which is connected here. And this MOSFET is in the diode connected form because the gate and the source are being shorted. Now here, if you see, the last two transistors input is provided from the gate of this particular first MOSFET. If you see, these two are getting input from here. And the sizing of the MOSFETs, I'm going to push all the MOSFETs in a similar sizing fashion, which is basically 10 microampere by 10 by 10 micro. That is basically WY is equal to 1. If you see 10 micro by 10 micro, but the first one here, I'm going to take the 1/4 the value of these particular value. If you see 10 micro, 1/4 of that would be 2.5 micro. I'll put the reason sometime later why this is being done. But as of now, you can just figure out why this is being given. So 2.5 macro is the size. Apart from that, there is no much major change. This is the same input, the VDS source which I have given with the DC value of VDS, which I'm going to give in the ADL window. Magnitude is being 1 volt, and 10 micro is the current. So let's try to launch this ADL window and do similar kind of operation what we did just now. Point 9 analysis. First, let's try to figure out DC analysis and figure out whether I am able to get the constant current and the output being 0 to 1.8. Let's try to do that. And outputs to be plotted. This is my output that is to be plotted. Yeah. Basically, this action, DC analysis, would fetch me the ID versus VDS graph, which is going to tell me whether my current is getting populated to 10 microampere or not, because my reference current was 10 microampere. So if you see here, yeah, you see it's exactly 10 microampere. And if I just press V vertical line and I mark it to a of 900 millivolt exactly at the center line, and if I see it's exactly 10.0204 microampere, which means exactly 10 microampere, which I am going to populate it over here. Fantastic. Basically, this 10 microampere is being mirrored over here. So that means this particular cascode, low voltage cascode current mirror is even more rigid than the cascode current mirror itself, because in the cascode current mirror, if we saw here the output here was the current somewhat lesser than the reference current. It was coming out to be somewhere around 9.8, 9.9. But here, for the same value of W by L, I'm seeing an exact value of current being replicated over here. So that's basically one of the advantage. So let's try to get into AC analysis and figure out what is the resistance, output resistance it is going to get me. I'll disable the DC. Let's run it. Let's push it to the calculator. My this would fetch me the so I'm going to get a value of 134 mega ohm. So that's my resistance of this particular low voltage cascode current mirror circuit. So that's what I got out over here. So this is one thing. And then and close these things. Now let's try to find out the region of operation. Now to do that, I need to go to the results, sorry, outputs, setup, region of operation for the upper transistor. Click on the expression, open the calculator, clear the calculator, click on OPT, come over here, click on this particular MOSFET, open this and click on the region. So where is my region? Let's see. And then go back to this setting and say get expression and say add. Okay, so these exercise we are supposed to do it. And anyhow, already this is being marked as an M3. So let me take it as an M1. So I'll just take it as an M1 here. And then I'll go back to my virtuoso window. And again, get into outputs, setup, region of operation for the down transistors. Here, I'll just say get expression because I already changed it in the calculator. If I do it instead of an M3, it should now fetch me an M1. Yeah, there it is. I say add, and I say okay. I'll close all these things. Now I think should be able to get the region of operation. So to do the region of operation for this, we should be doing the parametric analysis. So for that, go to tool, parametric analysis. Variable should be expanded or should be flipped from 0 to 1.8 in a linear steps with a step count of 0.1. I'll say okay. Once we do this, here also we should be able to see the region of operation curves. Just a moment. So I think we also included this DC analysis, right? We don't need this one. Just need to have let's try it one more time. Just a moment. Let's try to close this. So we'll ensure these two. I'll just enable the ROP and RON results, tools, parametric analysis, add variables from 0 to 1.8, a step of 0.1. Yeah, there you go. Because I enabled that AC and DC analysis, so it was picking up those analysis. So I just want this region of operation. Now, if you see for your previous schematic where it was giving you, or it was taking the value of the voltage. Basically, this indicates the voltage at which this MOSFET and this MOSFET will enter into saturation region. And I need to figure out a common voltage at which when both the transistors will be in the saturation region. So this is the region in which, see, why, how do I say this is in the saturation region? If you see 2 is being mentioned over here, 2 means saturation region. And if you see here, 1 means it's in the linear region. So from here to here, it is slowly entering into saturation region. And this is the point at which both the MOSFETs, that is the upper and the below, lower MOSFETs, down MOSFET, would be in saturation region. And what is that voltage at which these two MOSFETs would be in saturation region? Close to, in fact, it is exactly 600 exactly at 600 millivolts. So that's how you reduce the output voltage. And if you see over here, for the same schematic, when we did it for the simple cascode current mirror, it was coming around 700 or 800 millivolts, but whereas here it is coming down to 600 millivolts. So that means my this low voltage cascode current mirror is going to perfectly work at a lower voltage as compared to a simple cascode current mirror with an additional transistors, which is beneficial, so that my MOSFETs would be pushed into the saturation region as early as possible, giving me the benefit of expecting the current at a lower voltages as compared to cascode current mirror. So low voltage cascode current mirror is one such example where we can see the current mirroring or constant currents would be flowing at a lower voltages. So this is how basically the low voltage cascode current mirror is going to work. Yeah, so this is it from this session. So I just wanted you to basically try to practice these things because we had a long gap. So try to work on to these things and try to figure out the set of examples, and maybe in the subsequent sessions, maybe we are left with another 5 to 6 sessions. So we'll try to cover up all the labs and projects kind of things. And in the meantime, do practice. I have already pushed in all the these things in uh, the Google Drive. So ensure that you're going to